you for everything.
What's up, everyone? Welcome to this 10-part CO2 unfiltered series. I'm super pumped up. I'm super happy that you're all here. Looking forward to diving in with experts from all around the world on CO2 and why I'm doing this. I really want to bring you a huge amount of value from these experts. I know so many people in the industry, and we really want to help you as a technician in the field to be able to install CO2 better, work on it, service it, maintain it, commissioning. And I want to bring you this series from Refrigeration Mentor to really help you grow your knowledge. CO2 is continuing to grow around the world, and this is what we train on consistently with contractors and technicians around the world. And we really want you to and help you level up your game with CO2. This week we're diving into CO2 pumps, secondary systems, liquid overfeed systems, whatever you call it. We're using pumps to move CO2 liquid to cool and remove heat from different areas of a system, different applications. We have an expert here, my good friend Ernesto Rodriguez, and we're going to be
Good
diving
afternoon.
um, into their pumps, hermetic pumps. And I really, I worked on these systems in when I started out in the industry. I had worked on one liquid overfeed myself back in 2012, and since then I've trained lots of different people on overfeed system or liquid pump system or secondary CO2 systems. And what I didn't know about is how to install them properly. Honestly, when I started, I didn't know how to test them. I didn't know how to check the gallons per minute or the flow. I didn't know any of that stuff. You know what I mean? And this is why I'm bringing the expert. Ernesto, welcome to CO2 Unfiltered. How are you doing, my friend?
Oh, thank you very much for everybody. I'm available. Well, I'm here to explain what is the basic problems with pumping CO2. Thank you for your time, and I'm going to start my presentation. Basically, my presentation is to how's design, how is installation, operation, and prevention or refrigeration failures of the pump. But basically, we're going to talk about hermetic pumps. What is hermetic pumps type? Okay, hermetic pump is a no seal pump. We don't have any mechanical seals on this pump. We have two different designs. We have external recirculation and internal recirculation. External recirculation is a very good design, very good engineering. The only difference is we have the suction of the pump and the discharge of the pump, and part of the fluid go through the pump to the rear to the pump to cool and lubricate the pump. Internal circulation basically is everything is internally. We don't have any external piping, anything to cool and lubricate the pump. Basically, it's internally. We have you can see everything is inside. I want to explain how operate the difference with the system. The external circulation system, you can see we have the vessel and we have the piping. The external piping go back to the vessel on the external part of the circulator. Now, internal circulation, we save all this piping. In some point, we have the standard pump installation with no any extra piping and anything. This is the
Yep.
typical installation for internal external recirculation.
Yep.
Okay, how to operate the flow? Okay, in our pumps, basically we have two types of pumps, one impeller and multi-impeller. Okay, the one impeller, I want to explain how is the fluid runs inside the pump. Basically, we have the pump, the pump, the suction, and the refrigerant run to the pump, and we have a go to the shaft. We have a hollow shaft and go exactly direct to this impeller. This impeller is going to increase the differential pressure approximately 10 psi differential. Means this fluid is going to recirculate inside the pump, lubricate and cool the pump internally. We have this diagram, basically how operate, what is more basic way to operate. We have the cutaway of the pump. We have the stator, it's lubricate the carbon bearings. We use carbon bearings for this application because we use hydrostatic suspension, means the same refrigerant, the same is going to maintain and lubricate. It's like it happened with the internal combustion motor. You have the crankshaft, you have the oil, the bearings maintain the crankshaft suspended by hydrostatic fluid. This is
Yep.
exactly the same principles, okay? And for example, you can see the shield. These shields prevent the refrigerant go through the winding of the motor to prevent any system. But you can see the flow is free flow direct to the discharge of the pump.
Okay,
Now
so
we
the
have
the liquid doesn't go over the windings itself, but that's a
exactly.
protection area. Okay, and when it goes through the crankshaft, is there any possible way that that can get plugged up? Because you always have a 10 psi differential. That's how we can move it back in, right, to cool the motor. Is there any possible way that that could get plugged up on a CO2 system? Because I'm pretty sure you mentioned to me on an ammonia system, oil could plug up that crankshaft. Is that correct?
Yes. Yes, correct. Basically, oil is the problem because when you have a different density of the fluids, for example, oil, and the oil in low temps is very thick in ammonia. In CO2, we don't have this problem, basically.
Okay.
It runs freely. The only problem we have is a flash gas. We can't to prevent the flash gas. The problem is can do no make the lubrication correctly and the cooling correctly. I want to explain what is the problems or the causes of the flash gas for CO2. This is a critical situation for CO2 versus the
Definitely
oil
stick
refrigerants.
around. Definitely stick around. We'll get into that on the flash gas and how to prevent that stuff. So,
Yeah, exactly. It's correct. We can see how the multi-impeller pump runs. Okay, why we have two different designs? I want to explain in the next slide what exactly. The fluids run opposite because we have a high pressure on the discharge, and we will try to get the differential pressure. We have calculate approximately the 10 psi differential pressure from the discharge, and the internal part of the pump. Right here is the approximately 10 psi. We have this diagram to show P1 is in 5 and P2 is number 3. Basically, P1 is higher. We calculated 10 psi differential, and you can see runs through to the shaft, and we have a little orifice right here, and this orifice is going to make the lubrication of the pump. We can see in this cutaway the orifice right here. This orifice means you have the discharge of the pump. We have high pressure right here, and go direct to the bearings, go to the lubricate the pump, and go back inside the shaft. And this is the way the refrigerant return and back and start make the process or circulation. It's very simple design. It's not complicated. To disassemble the pump is very simple. You can see it's only a few parts. Okay.
so that's a quick question for me. I haven't pulled one of these pumps. If you go back to that last picture, so there is times when we talk about it later when you get flash gas or cavitation. I've heard before where it could damage up the impellers. And these impellers, can they be repaired or replaced? And we'll get into that later. But I just want to know, can they be if I get one damaged, can I pull this pump apart, change those impellers, and not have to change the motor?
Well, basically, the pump for safety to damage the most, keep the high damage of the impellers, we have the bearings, carbon bearings. When we have the cavitation, we have a lack of lubrication on the bearings. The bearings start wearing down because it's this differential and on the gap from the bearing and the shaft, the pressure of the pump start decreasing, and the pump is going to stop. Basically, when you have a problem with cavitation, the main problem is to replace the bearings, and is the majority to fix this problem is only bearing replacement and gasket replacement. In some when very rare situations, the impellers can be damaged, but it's very rare. Basically, the pump
Okay.
stops itself when the bearings are damaged.
So the bearings could be damaged by cavitation or pressure differential, and then we can actually, as a technician, I can actually pull this apart and change the bearings if the motor's still good, and get that pump up and running without having to get a new pump. Is that correct?
Yeah, exactly. It's correct.
Awesome. That's
Or
amazing.
replace the impellers, basically. It's
Yeah.
only just replace the bearings and the gaskets. It's very simple
Yeah.
to maintain this pump. Okay, let's go to the next slide. What is the difference with the one impeller and multi-impeller? Well, I can explain right here. One impeller pump is very good for mass flow. We can move more mass flow with one impeller pump versus the multi-impeller. Multi-impeller is not really good to move too much flow. But the advantage with the multi-impeller, we have a very high differential pressure. For example, we have in this sample 75 meters, 246 feet versus 175 and 574 feet. That is the advantage we have with the multi-impeller pump.
So let me so I understand this. So a single stage flow rate, you can get a higher flow. So third, let's say three up to 374 gallons per minute or 85 cubic meters an hour,
Mhm.
but it cannot move as much head. It can't move as high. Is that right? Like
Yeah,
the
it's correct. It's
okay,
correct.
but you get a bigger flow rate, but you can't move at is as high. The total dynamic head feet of head or head of feet. Is that right? Is that how?
Yes, it's head. The head.
Okay.
Some different pump manufacturers use to compensate this problem. They build the pump with a big, huge volute, big, huge impeller, increase the size of the impeller.
Okay.
In or only engineering try to keep the pump compact. This is the way we do. Okay.
Okay. Beautiful.
Next slide. This is the typical installation of the pump. We have level control on a vortex eliminator, and we have this protection. We have a different type of protector pump. This is the pressure stat. Differential pressure that prevents cavitation for low differential pressure or prevents high differential pressure. I want to explain in the next slides how operate this. We have the discharge of the pump. We have optional constant flow regulator. We have the orifice and differential pressure regulator. I want to explain in the next slide how operate those. What's the advantage of these accessories? Okay, pressure differential pressure switch. Most of the companies try to go to the basics. They don't want to have PLCs or moon controllers. They have a very simple system to control. The pressure stat is the best, cheaper way to protect the pump. When we have a very low differential pressure, the pressure stat is immediately send the signal and stop the pump when it start cavitating for low pressure or it start getting too high differential pressure. The same way the pump is going to, the pressure stat is going to send a signal to stop the pump.
Okay, so now like I do a chiller training, and in the chiller training, it's on glycol, so not CO2 at this point in this system. But that differential pressure can increase sometimes if the all of a sudden if the suction line is too long, or if that like squishes down, like it overheats and it gets smaller, and which will drop the suction pressure. Is that that's what you're talking about? That differential pressure from the suction to the discharge?
Basically, when you have low differential pressure, it's because the pump is cavitating. Is the main thing. When the pump is cavitating, the differential pressure across the pump is minimized, and the pump is going to stop before
Stop.
any more damage. Okay.
And that's the whole
Uh,
purpose of this device is that we don't
yeah,
want to damage the
exactly.
pipe because the
Yes,
pressure drops off.
yes, exactly. The main thing is prevent the pump to cavitate, and for the low pressure and the high pressure. I want to explain the next slide.
Okay, so
What is the
yeah, I just want to be
protection we
clear.
have?
I didn't want to mix everyone up. So this is for low pressure. So if the
Yeah, correct.
pressure is low between the suction and discharge, perfect.
Yeah, correct. Mhm. All pumps, all hermetic pumps is coming with thermistors. The thermistors are a device to protect the winding of the motor to overheat. When we can increase the temperature, the thermistor is going to open and shoot out the pump. Basically, we can use a controller. We have type of controller. We can some companies use PLCs to
Yep.
connect the thermistors, or we can separate offer this controller. This controller basically is able to stop the pump when it's overheated. We have the wiring diagram right here, which is for 220 or 440, plus ground, plus cable 5 and 6 are the ones to connect it to the controller. Okay, we have T1 and T2. We have the thermistor, and T1, T2 is where the thermistors need to be connected to prevent is anything increase on temperature on the winding immediately the pump is going to stop to prevent any damage in the motor. Mhm.
So now this here, the things that would cause this is high current, would be bad bearings.
Yes, can
Um,
be
what else, guys?
extra
If you want to go back to the
excess
last,
or mass flow. Maybe it's too much flow
too much
going through the
flow.
pump. Yes, and exceed the capacity of the motor or the mass flow capacity of the motor.
And so,
and maybe cavitation, and it's many
cavitation.
factors can affect it.
So what we want to do as a technician, we want to take our amp clamp out, put it on the motor, and look at the rating plate that you guys put on that motor. And
Yes,
if
it's
we're
correct.
going over that, that is going to cause those resistors to increase in resistance, send a signal back to this controller, and open up the circuit to shut it down.
It's correct. It's
Okay,
correct.
perfect.
Okay, I want to explain right now. We talk about flashing. Okay, this is a good example. Majority of the systems right now they try to use frequency barriers to save energy. Those are excellent devices to control and save energy. We have a sample right here in this curve with a orifice. The pump is running normally, and we are consumption we have a 3.3 kilowatts. But we have this example with the BFD, and we have a consumption of 1.6 kilowatts. That's an excellent device, but it's a very tricky to use BFDs when you basically use CO2. Okay, we have this example. I start a pump in a big company. This pump is going to run with a high differential pressure. Okay, the system was the pump was sized for 52 hertz, means the pump is going to run efficiently 52 hertz. Don't move it. You start the pump, keep it in 52 hertz. Most of the companies try to increase or reduce the hertz to control the flow capacity for substar or depends the application. But in the way I can see any pump manufacturer when they size the pump, for refrigeration, you need to keep the hertz is designed. In this situation, we have the people the technicians start increasing the hertz to 56 hertz. I say they show the curve on the pump, and we have this flashing. I say, what is that? They enlarge the curve, and we have this. This is flash gas inside the pump. I say, you guys are doing, don't do that. Go back to 52 hertz. Means you can see right here, the motor is set for 30 amps.
Yep.
30 amps is the maximum. This is the nameplate of the motor. That is the 30 amps. You check the amp meter, and it's very close to the ampere, and the capacity, maximum capacity of the motor. That is a big problem. I asked how much the amps in this application. They say we have 32 amps. I said, no, 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 no. You overheating the pump. Go back to
Okay.
52 hertz. And this
So
is a
this,
very good sample.
so because I see this a lot. There's val drives on pumps all the time. Glycol, CO2, it doesn't matter. We're talking about CO2. So we got a drive on the this pump. You're saying that when you design a CO2 system, you're designing at a specific hertz, so that flow is going to stay all the whole time. And there's other ways to manage the flow in the system, right? Besides the
It's
drive
correct.
up and down. Okay,
It's
and so
correct.
now that if we move up, if it's designed for 52 hertz and now we move that up to 55 hertz, we'll say now, because
Hmm.
now we got more hertz, more work on the motor, our amps will go up. That amps go
Yeah,
up, start to cause heat because we're generating more heat in the stator, and that heat,
yeah.
as that starts to go through, because we said that liquid goes and cools the motor, that here will
Hmm.
start to flash the CO2. Is that kind
It's
of what you're
correct.
getting at?
Hmm.
Perfect.
Yes, correct.
Okay.
Yeah, those flashing is the number one, and it's 90% of the problems with CO2 pumps are flashing. This is the reason I want to show this slide to be
Yeah, I
careful
love it.
when use BFDs. Don't be careful. It's excellent device, but you need to be careful when you application. Okay, let's go back to the CO2. Basically, we have a pump for capacities uh, for CO2. Okay, 52 bars is the most standard capacity. Okay, between 50 to 59 Fahrenheit or 10 to 15 Celsius degrees. This is the typical installation for a cascade system. We have the CO2 pump plus the ammonia.
Yeah,
Okay.
I see lots of these applications now. We got ammonia on the top side to lower the charge for ammonia, and then now we got CO2 pumping through the facility as
Yeah,
well.
it's correct.
Yeah,
What is the advantage we have with this cascade system? Basically, uh, we can save more energy, saving 20% approximate in energy savings. Um, the rate for recirculation versus other refrigerant, for example, ammonia, you can go 4-to-1, 3-to-1 recirculations. Basically, in CO2, it's when you size the pump, it's 2.1 to 1.5, maximum 2 two recirculations per minute. What does the circulation mean? Basically, when the pump recirculates the flow to the heat exchanger, to the coil, means you have 2 parts of liquid and 1 part of gas. How much you increase the flow of the pump, you want to increase this rate. It's going to be 3 parts of liquid and 1 part of gas. Basically, we want to keep very low for CO2 to prevent flushing, and the design of the coils already is the best way to run the pumps. Okay. And also, the advantage for the CO2 pump is very respond more faster for load changes for any application in the system. And the basic, we need to use filter and dry for CO2,
Yeah.
CO2 pumps. Basically, for the CO2 system, moisture is the big problem, no oil. In
Yeah.
ammonia is the oil, and CO2 is the moisture, the water. Mhm. Okay, we have a cutaway for the pump. Basically, the multi-stage pump, like I explained before, which is a very strong volute to able to support 52 bar. It's the most standard pump. We have also application for 40 bar when the temperatures are very low. Don't exceed the 52 bar. We can use the 40 bar. It's the standard pump and it's more accessible. We have a new pump. The new pump is for 65 bar. And the pressure test is for 95 bar. Is a new pump is coming to the market for also for special applications. Mhm. Okay, how the pump is moving, how the vapor is created inside the pump. Basically, I showed the diagram how the fluid is moving inside the pump, but we have gas. We can to prevent this gas flash inside the pump. Okay, we can see the number 4 is the highest pressure on the system because in the in one impeller pump because this is the way we increase the pressure to go back and move the refrigerant. Okay, basically when we run the pump to prevent the flushing, we want to prevent this gas phase on the CO2 pump. The same way for the multi-stage. Multi-stage is more better for CO2 application versus the single stage. You see, we have those high peaks or pressure. This is the multi-stage is more stable. We have the curve is more stable to prevent this gas or flash gas start building inside the pump. We have a very special application for example, lately for some special application of CO2, we need a very low flow rate and a high differential pressure. This is an example how using pump in series, two pumps in series to meet this low flow, 9 gallons per minute and 400 feet. This is very special. I see it most in data centers, in some petrochemical applications. I don't know, some of my friends, technicians, have experience with this application, but it's very special. We can do
So
that.
I got a so I got a question in this picture here because I know we've talked about it before. We don't want any short radius. We don't want to be curving right away because we could cause issues with like going into the circuit. When you have it set up like this, there's no issues with this pumping directly into the next pump with that 90 there with only having about 4 or 6 inches,
Yes.
away from each pump is, or do you have to have it a longer distance away, like 4 feet, so you don't have any cavitation or like turbulence, things like that?
Yeah, this is basically when you have a very long distance or the process require very high head of the pump and very low flow. You see the flow is very low to prevent
Yeah.
the flashing gas inside the pump. We need to use this type of application. Maintain the flow running across the pump, cooling, and maintain the high differential pressure. Okay.
Okay.
Okay, before I enter the Qmin and Qmax, I would like to go to how the presentation, how size the pump.
Yeah,
Basically,
let's
we talk
size a
about
pump.
pumps, but
Yeah,
we don't know how size the pump. You can go direct to the website and go to refrigeration and go to pump design, and basically you can get a start selection and you can request access. You can add the information about your
yep,
company, your name, everything
yep,
information, and send it. And maybe 15 or 20 minutes, you have a passcode to access. It's very free. Everybody can
yep.
access this program with no problem. Okay.
Beautiful.
Okay, now let's go back to talking about high flow, low flow, flashing gas. Okay, well, it's talking too much. But how we know? Okay, we have this program. Our program is very friendly to use for CO2. We have an example for CO2. Okay, we have a pump where it's going to handle 22 gallons per minute. Head maybe differential pressure 31 psi, 65 feet head, and the capacity is giving a horsepower, okay? Minus 40 Fahrenheit. For example, we need to go to 60 hertz, okay? Okay, the circulation is going to be 2 to 1, okay? Okay, the suction, the NPCH is the height of the suction of the pump.
So
Basically,
yeah,
I like to go, yes,
yeah.
sir.
What is that again? Like, so this is something that's really important. A net positive suction, right? Head. That is something
Yes.
really important. A lot of people don't know or even check that. What is that, and why is that important to know about when you're dealing with a pump?
Well, basically, you need to have the good level of liquid on the suction the pump. When you start the pump, it's going to get start getting fluid from the vessel and prevent the cavitation, basically. And according with the system, with your system requiring high load or low loads, the pump is going to respond to move how many capacity of liquid you need the system, and those changes in capacity also required to keep a level steady, a very static level on the suction of the pump. Plus, sometimes we have when they started the frosting system, when the regulator valve opens to release the hot gas back to the vessel, we have pressure differentials sometimes. And to prevent those turbulence when we have a differential pressure when we have defrosting of some loads, we need to keep a very good safe the pump to prevent this cavitation. In this
Yeah.
situation, we have
So
a. Mhm.
if we have a drop in the net, the NPSHA, so net positive
Yes.
suction head,
Mhm.
if we have a drop in that, that can cut. If we get too low on our chart, that could cause cavitation. Is that right?
Well, I go to size law, for example.
Yeah.
I want to go 5 feet. It's
Yeah.
exactly it's a 1.5 meter. Means the pump is going to run. The safety of the pump minimum is going to be 1.5 meter. I can go with 3 feet.
Okay.
Sometimes in some applications you need to size the pump with very low level, 3 feet. Prevents means the pump is going to handle very low levels without cavitation. I size the pump to handle very low levels. In this
Okay.
example, I want to go to 5 feet.
Yep.
It's approximately 1.5 meter. Okay.
Yep.
Okay. Now we have an option to Qmax, flow control valve, or a frequency barrier or frequency control. I want to run the three options for you guys to see exactly how the thing is it's going to work. Okay, I want to go to the orifice, Qmax. Okay, we run sample right now. The program is selecting which pumps we need.
And inside this program, we've already checked it. There's different units. So if you want to do it in cubic meters or gallons
Yes.
per minute, so you can change all that stuff.
Yeah, I want to explain it in a few minutes when I go back to the main screen. For example, in these options, we have this pump is one impeller is very close to the curve. It's not really it's very tight. You can see right here, it's really tight, and the pump right here, the pressure is too high. Let's go to the cam to three. It's much better pump application. See,
Okay, so
we
that
can we can
orange area, you don't want to be touching that. You don't want to be in there, right? The
no.
orange. Okay, so
The
that's where
orange
cavitation
means
will happen. that
Yeah,
area?
the orange means is you exceed the capacity of the motor. The
Okay.
motor is for 3 HP, for example. If you pumping too much fluid, it's going to exceed the mass flow capacity of the pump. And that orange is the cumin, is how many liquid is going to return to the vessel. For example, in this sample, it's going to return to the vessel approximately 8 gallons per minute, and the maximum flow of the pump is 50 gallons per minute with no problem. Okay.
Okay.
Now let's go back to the main, and we can switch US, and we can switch international or hermetic. Okay, I will keep hermetic. Give me the capacity in cubic meters, for example. We have bars and cubic meters. Okay, flow. Okay, and I go back to US. It's very friendly program.
Yeah, beautiful.
Okay. Now let's go to frequency controller. Okay, let's go to frequency controller, and you can see what selection is going to be. Okay. Okay. We have these many samples. Okay. We have the smart, watch smart. Okay. You can see this is beta, it's got too low. We're going to find the curve is more friendly for the application. Okay. I will like, this is a 32 hertz, 30 hertz, uh, 29 hertz. Okay, 36 hertz. You can see 36 hertz. The curve is much better the application. I would like to use this pump because we have
So
36 hertz, and
yeah.
you can see is inside the red
Okay.
area.
Yeah.
Mhm.
So we're trying to get inside
Yeah,
the
don't be too
efficiency curve.
close. Yeah, don't be too close. Okay, this is the best application. We have different ones. These are different options. When you select it, you try to select the best option. See? It's the advantage with this program. You can select many pumps, and you can see what is the best application for. In this selection, I think so. This is the best pump for the application. Let's go back, and let's go to the flow control. Wow. I want to explain what is the flow control valve in the
Yeah.
next slide. Okay. See, it's a different. We have a single impeller pump, the CNFs, and the cams are multi-impeller. Okay, the single pair is good application means we have the application right here, and we can play more with the pressure. I want to explain how the control valve work. We can have this pump. This is the optimum operation of the pump, but we have this area to the valve control how many pressure is demanding your system for many evaporators, many coils, or single coil. I want to explain in next slide in the presentation exactly how the
Yep.
thing work. Okay.
Because that distance there, that means in our design condition, we're at about 62 feet ahead approximately, but we can
Yeah.
go up to almost 100, I guess, or 90,
Yes,
like
we can
95.
go. Yes.
We got
Yes,
that much
correct.
range to play with when we're
Mhm.
loading and unloading different cases and at
Yes.
defrost and not defrost, things like that. Okay, beautiful.
Yeah, the regulator control and all this see how the system is demanding liquid. Okay. Let's go back to my presentation. Okay. We have, I talk about Qmin. Okay, this is the Qmin, Qmax. We control with the orifice, we control the flow of the pump to prevent to go to the orange area. The orifice is already sized for the capacity, for example, and on the person on the program, which is for some flow, 60 gallons per minute. This orifice is all sized to work with 60 gallons per minute is the best way to work, and it not want to exceed the mass flow to overheat the motor and maintain your system running perfectly. Now we have the flow regulator. The flow regulator is a device installed in the pump discharge. Basically, it's a control valve with a V port and with the spring. Basically, when the system is demanding too much fluid, the port is going to be open. But in some point, you have multiple coils, multiple evaporators. and in some point is demanding too much liquid, too much liquid. But the problem when you have too much liquid, you want to have unbalance the pressure on the coils. Means in coil number one you have pressure a higher versus the coil number three, and you have a lack of liquid and multiple evaporators. How the thing works? Basically, I have it right here. Okay, the regulator, the pump is pumping the fluid. It's okay. The system is equalized, the balance, the coils are perfectly. But at some point, the system is demanding more fluid. More fluid means the pressure is going to increase on the coil or the evaporator is closer to the pump, to the less drop pressure. To prevent this problem, to have more pressure in coil, also tunnel number one and tunnel number three have lower, this is going to be more modulate and equalize all the pressure in on the tunnels. Any
Okay, so
question?
this will be on different circuits then. Is that
Yes.
that
Well,
correct? And is this always used, or do you see it not being used? And because that's an advantage, I would say. But where do you see it used mostly? And when would someone be
and
like, man, I should be using these versus not using these?
a special application where you have multiple tunnels, multiple coils, multiple heat exchangers. Mhm.
Okay, well, in supermarket application where I see some of these, there's hundreds of coils. You know what I mean? So
Yeah, yeah, yeah. Mhm.
so this would be in the liquid line going to it, like the supply line.
Yeah,
Okay.
yeah, discharge of the pump. Okay. And it's to prevent this unbalance. So you see, when you have multiple evaporators, sometimes evaporators closest to the pump is higher pressure, and the ones far away, the pressure is low. This is
Yeah.
prevent to balance the pressure in the system.
Great.
This is the charge we have here with the Qmax. Okay. You see the curve is decreasing uh, constantly, okay, to the max capacity of the pump. This is the regulator. The regulator we can play more with pressures, okay? And this is the area is dangerous. You can to operate this exceed is the dangerous area for the pump.
This is when you exceed like the net positive suction.
Yes, for example, you requiring to pump in too much liquid, and the vessel start getting empty because you pumping excess of liquid versus the capacity of the recirculator, and you
Yeah.
empty the recirculator and the pumps are cavitating.
I do have a question here from Darwin. What is the difference between NPSHA and NPSHR? Do you know? Is there a difference, or do you know?
Okay, R is the A is the when the level on the pump. We have the pump, we have the liquid level. R is when you have the level when the liquid just go across the pump. It's like a differential. It's when you size the differential pressure of the pump. Basically, is R. Is the difference. Okay.
Okay, so one
Mhm.
is the level, and then one's the differential. Is that
Yes, basically.
basically?
When the pump is running, you start getting a liquid with some differential pressure. The liquid is going to vary.
Oh,
The level is going to change a little bit.
yep.
Basically, you need to calculate the pitches are when the pump is working and when the liquid is when the pump is static. Okay, that
Oh,
is the difference.
perfect. So static or running. Okay,
Yeah, correct. That is the
perfect.
most basic. Okay. Now we have the return of the pump, the painting, the Q main. This we have the pressure stat. The pressure stat also works for high differential pressure. Means you have too much. For example, we have four tunnels. The four tunnels is going to demand 100 gallons per minute. Okay. In some point, tunnel number one is running, number three is stopped because it's loading the product, and number four is getting defrosting. Means the capacity of the pump is demanding only 50%, 50 gallons. And sometimes the pressure start increasing too much in under the discharge of the pump, and start we get a lack of lubrication in some point because of the high pressure. You set the pressure stat Oslo to stop when you have a high differential pressure. The Q main, like you see on the charts, is able to handle some maximum gallons per minute to return to the vessel. At some points, you have limits. When, for example, in those four tunnels, three stop for different reason, and it's only one running. Now the system is demanding 25 gallons per minute, but the pump is pumping 100 gallons per minute. We want to, it's some issues to how fix it. Okay. Now, when you sizing the bend line means is when you remove all the vapor or gas bubbles generated to the pump and also, like I said before, how return the liquid. You can size it according with the flow of the pump. Had 14 gallons per minute, half inch, 32 gallons per minute for three-quarter inch, all the way to one and a quarter for 185 gallons per minute. You need to be careful how sized this pipe.
So
Sometimes it's
that
undersized.
Yeah,
Mhm.
so that there is if you do on the discharge when it's coming out, if you get any bubbles or any flash gas, like
Yes,
and that there is going to vent it off into there. So that ball valve that I see up there, that could should never be closed. Is that correct? Like
yes,
locked
never
over?
closes. Uh-huh.
Because if you
And
close that, what
yes.
would happen? Just say if that's left closed by someone.
Oh, well, it's going to, in some point, the pump is going to be getting stop or high differential pressure
High
because,
differential.
for example, I say the system is not demanding too much liquid and the pump start getting high pressure on the discharge and going to stop for high differential pressure plus flash gas, those bubbles can go direct to your control valves, to the Teflon seats of your solenoid valves, damage the
Yeah.
solenoid valves, Teflon seats at some point.
And so this chart you would provide, this is in your manual or something for the
Yeah,
customer, like for that
yeah,
vent
and the
line.
manuals show everything.
Yeah, yeah. Okay,
How
great.
size it. Any question, we can provide
Could
information on
could
everything.
you oversize it? Just say it's a 14 gallon. Could I instead of a half inch and I put three quarter, would that be fine? Or
Yeah,
would
it's
that be an
okay.
issue?
Don't
Okay, just
oversize it. You can
just
you can
just
go
don't undersize
oversize.
it. Yep.
Yeah. And the orifice already have some diameter allow how many fluid returning. It's different pump manufacturer use a hand expansion valve. The difference with a hand expansion valve sometimes it's too wide open. It's sending too much liquid back to the vessel, and you have a lack of liquid on the system. This is the reason the German hermetic prefer use orifice versus hand expansion valves.
Okay, so that's a good point. So now if you have a hand expansion valve and you oversize it and someone leaves the valve open too much, it's going to reduce the gallons per minute out to the coils. Is that correct? Or the
Yes,
flow?
exactly.
Sorry. It's going to reduce the
It's
flow because
correct.
now the flow is going to be going back to your vessel versus going out to the
Mhm.
cases.
It's
Okay,
correct.
good.
Okay, I explain how the differential pressure regulator works. What's talking? We're talking about pumps. What he talking about valves? It's no logic. Okay, it's when in the way I work for a valve manufacturer for 20 years, and I found it's an harmonic work together. You work with a pump, you need to work with valves too. Okay. Now we have a regulator to make the pump to control these high peaks of pressure demand liquid or low pressure demands. Okay. And why? You can read right here how is exactly the advantage of the regulator. Okay, this is the regulator basically. Okay, well, let's go back to our four tunnels. We have 90 gallons per minute, 100 gallons per minute. At some point, three tunnels are stopped. You have 25 gallons per minute. The orifice is only handle a maximum capacity. It's have limits because it's an orifice. But in exceed, when you have an increase of pressure, we have this regulator is going to open. It's not relief regulator. It's a differential pressure regulator. Too much companies confuse relief regulator is when you have liquid a trap on between the check valve and the shutter valve to relieve the gas is getting on the liquid. This is a relief regulator. Differential pressure regulator, I want to explain how the thing work. Okay. For example, these are different manufacturers, Hansen, Parker, and Danfoss. This size to the best, the valve is going to the best, going to the recirculator, okay? And this is the pump discharge, okay? We want to calibrate the pump. Our pump is running with a 45 psi differential. We want to calibrate this regulator. We have the gauge right here, and we're going to open the stem a little bit by little until get the 45 differential on this regulator. Means When you exceed the pressure discharge on the pump, instead to the pump stop or high differential pressure, this liquid is going to return back to the vessel. And the regulator is going to size according to how many gallons per minute you want to move. It can be 3/4 inch, 1 inch, or 1 1/4 inch port. Okay, this is the advantage, the thing, is the beauty about this device. Means one more thing, you keep your pressure, your constant pressure. You want to have a pressure and your hand expansion valve on your system. You keep the pressure on your hand expansion. I want to explain in the next slide. Okay, for example, we have the pump. We have the hand expansion valve. You need to turn how many? Okay, 3 turns to keep the differential pressure across the valve. X differential pressure. When you reduce the pressure right here for a bypass, for BFD, sometimes they reduce the flow on the frequency barrier or use a bypass to compensate this flow instead of differential pressure regulator. The pressure and the enter of the hand expansion valve is going to minimize, means this valve is going to be the loss calibration because you calibrate this valve to have for example, 45 psi differential to maintain the liquid at the temperature in this evaporator. When you reduce the pressure right here, this loss calibration. The
Yeah.
same way with the motorized valve. Mhm.
Yeah, that makes sense. So, because you set it up for that specific flow of the pump, and now all of a sudden the pump doesn't have that flow because we dropped the flow because of a drive, and now we're not getting the same amount of flow through that coil because it's a hand expansion valve example.
Yeah,
Okay.
exactly. We're going to maintain difference PSI, the 40 PSI differential. Means you have a constant pressure on the pump discharge to go direct to your valves. The motorized valve is the same way. Instead to the motorized valve stay working normally, very soft. When you have this variation, the motorized valve start working like crazy. Boom, open and close. Try to compensate those pressure, drop pressure on the system. And in some point, you need to replace the motor because overworking or the seats, the Teflon seats of the valve. Okay, this is the beauty about Haptus pressure control device. Okay, what is the correct or incorrect about this? Okay, we don't need to have a very high drop pressure on the vessel. I want to explain why. We need to have a vortex breakers. The level controls can be far away from the suction of the pump. We need to have maybe it's going to be a level control for a stem, well, electronic control or those flow controls. And no turbulence is going to the suction of the pump. Keep the turbulences away, and also the bevel need to be on the 45 up and not 45 down because you suck bubbles on the system. Okay, normally when you have a valve and the installed close to the
So
pump,
before we go ahead, that differential pressure regulating valve that you say that an example was to set to 45 psi. The purpose of that is that if our pressure differential gets higher than 45, we want to bypass so we don't cause fluctuation in our evaporators. Is that correct?
yes,
Okay.
some companies use bypasses. Means the bypasses open a bypass to
Yep.
return the liquid back to the vessel. Mean the bypass, the disadvantage is you don't control the pressure. Means you need a constant pressure
Yep.
on your hand expansion valve. With the bypass, you reduce the pressure. The same way with the frequency barrier. Some companies reduce the hertz on the pump to reduce speed of pump and reduce the flow. Means problem number one, flash gas. Problem number two, you lost the balance in your system. That is the number two.
Because
Okay.
that's the big thing. We need to balance out a whole system to make sure
Mhm.
that all the flow is happening simultaneously correctly, even if there's defrost, no defrost, and as we continue to move that CO2.
Mhm. That's correct.
Okay, great.
Okay. For example, this will be a minimum 5 times the diameter of the pipe. For example, this pipe is 2 inches. The distance need to be 10 inches minimum. Okay.
And what can happen if
Uh,
you're not? That'll cause cavitation, maybe?
well, we have turbulence right here. We have turbulence. We don't need any turbulence on the suction of the pump.
Yep.
Okay. Can be cavitation, can be flash gas, anything. Any type
Perfect.
of turbulence can make any problem with the pump. And the same way with the suction, this is the eccentric and concentric. This is the best way to install it. Okay, let's go back to the pressure. Okay, We no need to keep this pressure drop. When we drop the pressure over 1 psi or 0.07 bar, the refrigerant start boiling inside the vessel. Means those bubbles will go back to the suction pump. For example, I have a sample from one contractor starting, they starting the system and call me, brand new pump the pump is cavitated. I say, what are you doing? I say, I starting the system. Okay, now this is my capacity. I need to go to the temperature of the system in today. I say, okay, wait. You need to keep it careful. You need to be 1 psi per minute. You're going to take maybe extra 2 or 3 hours. You need to go step by step because you're going to damage the pump. Okay. Okay. Now, the compressor, you sometimes the compressor is load unload too fast. For example, screw compressor, 65 is 100%, you reduce it to 60%, and you in some point if the compressor is running to 80% capacity and you go to 100% in one shot. Means in some point you're going to get some pressure differential on the vessel and start boiling and start getting noises on the pump, start getting some noises and
Yeah.
cavitation. Mhm.
Okay, so we have a Marco had a question. He says in ammonia pump systems, it's very common to have bubbles in the vessel when you pull down the pressure in the vessel quickly. The same happens in CO2 recirculate. So even in ammonia, should you be taking your time, 1 psi per minute, or is this just
Yes.
CO2?
No, I say an ammonia is normal. It's a big mistake. They need to be careful. Okay, don't exceed the ammonia. CO2 is more critical because CO2 have the tendency to flashing more versus ammonia. Okay,
But bubbles in
so
ammonia is still bad too, right? If you're starting to pull it down too
yes, any
fast, that's still going
bubbles.
to go into the motors do the same thing, right? If you get
Yes,
bubbles going in there because you're dropping the pressure too fast in the vessel and you see these bubbles, that's going to start cavitating that motor. You may not kill the motor right then or damage the motor right then, but that does damage. Either way, anytime it's like
yes,
a compressor, you do a little
yes.
bit of damage. That damage doesn't go away. It stays with the motor until you maintenance is repaired or replace it.
The rule is don't exceed 1 psi per minute in ammonia or CO2, 1 psi per minute. Don't exceed it. Okay.
Okay.
Elbows. Okay. One more issue. Elbows. Elbows create turbulence. Short radius elbows have this turbulence going back to the pump. Okay. We don't need elbows. I don't agree to have elbows on the suction of the pump. Okay. We have this sample right here. I think so this manufactured. They use long radius elbow for because maybe it's no option to do that. But this is no, it's going to work, but I don't agree too much. Okay, you see the elbow right here, right to the pump, and you can see in this X-rays how the turbulence is is getting to this turbulence is going to the suction of the pump.
So that was a question that we had, like what's most preferable bends for the suction, long or short radius? So that the best case there would be actually moving the pump probably 2 or 3 feet away with a
Yes,
straightaway
exactly.
and then a long radius elbow, not right at the
It's
pump.
correct. It's
Okay.
correct.
Is there is there
Okay.
any, is there any rule of thumbs of it should be like 3 to 1, the size of the pipe, like the other one, 5 to 1, or just a foot or 2 feet away?
Basically, we can use the same rule, five times the diameter to keep the
Okay,
turbulence. Okay,
great.
it's the same
There you
rule.
go.
Mhm.
Love it.
Okay, talking about ammonia, we have this problem.
That looks like
Typical ammonia have this oil. I have a customer call me, the pump is not increase any pressure. Okay, I say check the filter, remove it, and see what you see. Send me the video and oil. We go little side from now CO2 now ammonia. Ammonia, we have this big problem. Okay, this filter collapse because the oil. We need to be careful with install filters for ammonia. You can install filter for CO2 because it's more clean, but you need to have some type of monitor the differential pressure to keep preventing increase the differential pressure on the filter and damage the suction of the pump. Okay. One more problem, insulation. Okay. I use the same example, use the BFDs for this application. Okay. The guys call me, say the pump is damaged. Okay. What I mean the pump is damaged. Okay. Okay, send me the picture. Say, okay, what you did. Okay, send me the. Okay, you have insulated. Yeah, this is the insulation. I say, oh my God, it's overboard. He removed the insulation and say, don't insulate the pump. Why? Because the heat generated on the motor is going to keep it with the insulation and it's going to build flash gas inside the pump. Most CO2 is more critical versus ammonia. And we have a sample right here. This is a CO2 pump insulated, and at some point, call me that the pump is damaged, and I say, okay, this is the problem. The best way to run the pump is no insulation. The ice is going to help to cool the refrigerant and to cool the motor. Is the best way. Mhm.
Yeah,
Any
Marco had that
question?
question as well. He's like, "Do you recommend insulating or not?" So right there, you said, "Do not insulate." So
No, no insulated pump. That is the problem. You create flash gas in some applications. Okay. Okay. You need to keep the velocity on the suction of the pump. For example, for ammonia, it's 3 feet per second, and for CO2, it's 2.5 feet per second. Why I very specific on the suction. Well, when you technicians going to replace a pump have problems, you need to be careful on the what's pipe diameter on the suction of the pump. Because most of the problem, for example, I have a pump, buffalo pump replacing in South America. And I replace the buffalo pump is going to handle 75 gallons per minute. Okay. In some point, don't worry. I want to explain that, and I have more slides going to explain this situation in South America. Okay. Okay, we have a discharge line. Basically, when on this charge line, we need to keep 7 feet per minute for ammonia and 5 feet per minute for CO2. Okay, basically, we need to have a steady flow to or system to the head to the train of valves to all the system to the evaporators means the pump need to run perfectly. We have this table. Okay, this table is keeping this for CO2. It's 5 feet per second is the velocity you require to move enough liquid all the way to your system. 1 inch, for example, is good to handle 17 gallons per minute. You go over 17 gallons per minute, you go to next size, 27 gallons per minute. The same way for CO2. CO2, 1 inch is under the pump discharge is the maximum handle, 12 gallons per minute, all the way to 4 inches. Now, 196 gallons per minute for CO2 and 274 gallons per minute for ammonia. You undersize this pipe, you're going to have problems with the pump. Okay, the pump is no increase in the pressure. The pump is not making any noises. You need to be careful. Technicians need to be sure the diameter on the pump's discharge. How's the piping? It's very common problem. Many situations happen when the pump fail. I say, well, check the diameter on suction on the pump, discharge and suction, and they say, okay, it's too short or it's correct. Okay.
So this wouldn't be like, so after the installation contractor put it in, this would not be installation of the contractor. This would be actually on the pump skid usually, because when I go to a store, I look at the refrigeration legend and it shows the flow rate. So it could be 270 gallons for the main. That's
Yeah.
my main. So you're saying when someone designs a system, they're going to design it for all their loads, and they're going to be like, our main, I
Yes,
need 250 gallons. When they have
it's correct.
250 gallons for the main that we need to go out there, if you go back to the next slide, we need to make sure that we have a minimum, let's say 150 gallons. We need a 4 inch discharge line, you're saying, if it's
Yes,
150 gallons.
yes, exactly. 4 inch line. Okay. For
Okay,
CO2.
okay.
Mhm.
Yeah.
Be careful with sometimes the engineering is incorrect and undersize the piping. Okay. I
But
see the problem all the time.
but we don't want to
Okay.
oversize the a pipe either. Because if we went with a 6 inch pipe, we don't have the velocity we need. Is that correct? We don't want to
Yeah,
oversize it
yeah,
too
well,
much.
on the charge, yeah, you need to be more, you can sometimes oversize it, but you need to keep this rule, okay? Basically.
Yeah. So you need to keep 5 feet a second when you're doing the sizing, the velocity.
Yeah, exactly, for CO2, okay?
Yeah.
Okay, basically the suction is more critical. Okay, we have is on undersized. You can cause cavitation, prevent or okay, or create flash gas popping. Okay, and the suction you able to no exceed two size the pipe size according with the table we're going to show in a few minutes. Okay, don't undersize. Is no way. Don't you want to replace a pump or checking a pump is undersized. For example, this is the suction. Let's go back to the example I have in South America. Okay, they replace a buffalo pump. Install my pump, 75 gallons per minute. I say, okay. They call me, say the pump is not increasing pressure. I say, what I mean increasing pressure? Start getting, they send me the video, the gauge started getting up, in some point, fell and down. I say, okay, give me the information. I asked information and I found, okay, what is the suction diameter? 3 inches. I say, that is the problem. You need to go 4 inches. Why? Well, the other pump runs many years for 3 inches. I say, this is the reason you need to replace mechanical cells every 3 months or 6 months because this the problem with the undersized pipe. After they replace the size to 4 inches, and now is able to correct the problem. Okay.
So if you undersize the suction line, now our pressure differential gets higher. Is that correct? Or
Yes.
lower?
Uh-huh.
It gets
It's
higher?
high. Well, and when the pump is going to require some amount of liquid. Okay. When it's like you choking the pump. You
Yeah.
choking the pump and start getting flash gas and the the hermetic pumps, the advantage is when you don't have enough fluid or pressure, the pump is going to don't increase the pressure and going to shut down. You see the pressure increase, in some point, the pressure is going to decrease. In open type pumps, it's going to running, but the problem with open type pumps, you need to replace the seals constantly in very short time, maybe 3 months, maybe 6 months.
Yeah. And
When
that failure's due to overheating then of the pump or
I
what
Yeah,
usually,
I
or is
think
it
turbulence is a
turbulence?
mix. Turbulence,
Okay.
flashing gas, it's a lot of things happen where you choking undersize the suction of the pump. Mhm.
Okay, perfect.
This is the typical piping for pump, for a pump, for example, to keep the velocity. We have two pumps running parallel and one standby, and we need to keep this rule of thumb, the 3 feet per second. Okay. This is typical. This is for CO2. You see, it's in stainless steel. We have a valve box right here, and we keep the distance between the valve and the flange of the pump for 5 times minimum diameter. The diameter of the pipe, the distance to
Yep.
be 5 times. Okay. And the same way for multiple pumps, we have these multiple pumps, 4 pumps, and the same way. This is the typical way to do that.
I like the
I
headers and
have
stuff getting out.
a I have a issues right now. You technicians or people who's going to work with the pump, be careful because in some point customer call me. I need to go on with the pumps. I have problems with my pumps. I say, okay, before send me a picture on your vessel or diagram. Okay. First of all, the discharge of the vessel is right here, and we have the lake all the way here. I don't know the diameter of this pipe. I don't know which velocity. Means we have a problem right here. Now we have 3 pumps running. Okay. Now those pumps fight with each other. Okay. This is the reason it's replacing a pump right now because this pump, when this pump is running, can create turbulence and make this pump fail or this pump is running, keep those top pump empty, no enough fluid. Okay. That is a big mistake. If somebody's going to work with pumps in CO2 or ammonia, check why, and they have too much problem. Check the why, because this is a problem. The same different vessel right here is the same problem. The pipe diameter is too small. They don't maintain the velocity of the suction of the pump, and the pumps are failing. Okay, I see this many times.
Okay,
We call my
so in this example here, your first one that got an X on it, that's just one outlet of the vessel, and you're going to
yes,
multiple ponds, even though it's like piped evenly. You can run into like if it's distributed even. Like this first one that we're looking at, like the picture on the right hand side,
yes,
it comes down, and then that last pump. If all three pumps are working, that last pump might not even get any liquid. You know what I mean?
yes,
Like,
exactly. Mhm.
okay, but if you piped it down in a T and distributed it evenly, it's still not as good as if you have two outlets of the vessel. Is that
Yes,
correct?
exactly. Yeah, this is the reason, the rule. This is the best, this is the correct way to install the pumps, okay?
Okay,
The
yeah.
main leg and the three subsystems right here, okay? For
Okay.
multiple pumps.
Okay, cool.
Okay, we're talking about horizontal vessel. It's the same way. We have the pump, we have the vortex breaker, the way to collect dirt or oil, and it's very friendly, okay? This is a typical installation for CO2. We have the vessel and each pump. For example, we had the elbows right here. We're talking about elbows before. See the distance between the elbow and the suction of the pump?
Yep.
The ones I showed with the elbows was too close for the pump. Now, this is the correct way to keep an elbow and keep the distance to prevent any turbulence. Okay?
Yep. Because we don't want turbulence.
Yeah. I hope this help you to clear
Oh man,
any
I
myths
learned a
or any
ton.
questions
Yeah,
about
no, I
this.
got a ton of questions. So we got a few in here. Um, ba, ba, ba. So Darwin says very important feature in a pump illustration is that the flat on top eccentric reducer to avoid air pockets that will cause cavitation. Moreover, long radius is better due to low pressure drop compared to short radius. 100%. I agree with that. Okay, a few of the other questions. So when sizing the pump, we went through some of this, but when sizing the pump for a CO2 system, what are the key things technicians should look for beyond just the flow rate? You know what I mean, or the NPS? Like, what are all the things that they should look for when sizing pump?
Well, basically, when you are sizing the pump using the program, in case I use the flow, differential pressure, and the head of the pump,
Yep.
or the differential pressure you want to run, how the distance is going to work. Now, when you want to replace a pump or maintenance a pump and have a problems constantly, you need to be careful how it's installed. And the suction of the pipe, the discharge of the pipe, the distance between the shadow valves and the suction on the flange of the pump. It's a concentric or eccentric reduction. Is venting correctly. It isn't no turbulence when the suction of the pump, like I show on the drawings, is any prevent, go to the turbulence, the discharge of the vessel, go to the suction of the pump and create turbulence. We need to prevent any turbulence of the pump, any type, okay?
Okay, so
No,
one of the things that you said earlier is about there are some manufacturers that use a drive to change the flow. So they change the frequency to change the flow. When
yes,
you size it, you're saying like that example, you said 52 hertz. Okay, like
yes,
that's the way to pump, the most efficient run of that.
it's correct,
How
it's
do they
correct.
change the flow? Like, what is the device that they use to change and increase or decrease the flow if they're not using the drive?
I recommend the differential pressure regulator. I seen to petrochemicals. I don't want to say petrochemicals, major petrochemicals, or they have experience. The packages is coming from Europe,
Yep.
but they install VFDs. I say that is a problem. Or for example, one company tried to use the VFD to control the level of the vessel. If the vessel increase, they reduce the speed of the pump. Okay, if the level start demanding too much liquid, increase the speed of the pump, and they replace pump like crazy. I say this is not the way to do that. You need to have some type to control the level, but no control the level of the vessel using controlling the flow of the pump is a big mistake most for CO2. Where we did it before, yeah, but you're not pumping water, you're not pumping oil, you're pumping a thermodynamic fluid. That is the big problem. Bypasses. Some companies use bypasses. And CO2 basically is critical. They use a bypass when the heat exchanger is not demanding too much, it's quick demanding liquid. They open the bypass, start recirculate the liquid from the suction all the way to the discharge of the pump, and it starts flashing gas. The pump called me and say, we have problems with those pumps. I say, are not working. I say, after go over there and check the design, I say, this is the problem. You have the bypass. When you run the discharge of the pump, your system is not demanding liquid, and you open the bypass, this circulation means start you circulating constantly the CO2. You heat the CO2 and get bubbles. Those bubbles go to the suction of the pump. Try to be careful with wet passes, and you're going to have problems with the pump check if they control the flow with the frequency variable. Look, remember, frequency variables are excellent only with you size the pump and keep it and the size of the what design the pump. 52 hertz, 45 hertz, or whatever is the
Whatever it
capacity,
is.
but don't move it. Don't move
Okay.
it.
Great. So startup and commissionings, like what measurements should a technician take? So they just got to install, they just charge it up. And what are some of the conditions that they need to check? Because one of them, you said you don't want to drop the vessel pressure quicker than 1 psi per minute. I guess that would be one. But what are other things they need to check, like amps or flow verification? What are some of the things that they should do
Yeah,
during
check
commission?
the level of the flow. It's for example, we sizing for 1.5, and the program we sizing for 1.5 minimum flow. Normally, you keep 2 feet or 3 feet higher. Check the level. And is the level is higher is exceed 2 feet or 2 feet from the design of the pump. We design the pump 1 point with 5 feet. Okay, check the level of the vessel for 7 feet. It's a security. Before you start the pump, we just check the level, how the level of the liquid, check of all the valves are open, the return valve for the cumin is open. What else? You have filters for ammonia. I recommend that you run the filter only for 72 hours for ammonia because all the oil remove the filter, remove the mesh. Keep the filter, but remove the mesh after 272 hours. For CO2 is different. For CO2 can run totally all the time, but the best way is to keep a differential pressure gauge to see how the differential pressure across the filter is one more point. And check if the thermistors are connected. The pump have thermistor, check the thermistor are connected, check the calibration of the pressure stat, or check the calibration of the PLC. How is the minimum pressure to start getting cavitation? The pump need to be shut down. Okay, depends is pressure stat or PLC system. Those are the main factors.
Okay, great. So now a system has been running for a long time. You got the maintenance team in there as technician. What are like some of the critical maintenance items to really check in these pumps? Like flashing, we talked about. If you start hearing noise, that's something you want to take a look at. I guess, matching it up to the amps, checking your differential. What are a few other maintenance things? I guess the filter you said already, checking the pressure differential across the inlet filter. Is there any other maintenance things that they should check? Because this is important. I think this is what's missed. Like people just going, oh, the pump's running is okay, but actually we need to go and take some measurements. Is the voltage right? Is the amps on par with what the pump says? Is there any other maintenance tips that you can give?
Well, basically, if the pump is in hermetic pumps, as I say, if the pump is running, don't touch it. If you see the pump is running smooth, there's no noises, don't touch it, don't open it. Well, I have a 1 year maintenance. I need to do that. I say, well, the pump is running, yes. Any problems? No. Leave it. Don't open it, because sometimes when you open the pump, sometimes you can make a mistake when put it back together or something's happened. Okay, basically you check if the system is, the parameters, that everything is correct, but basically my recommendation is the pump is running. Well, we need to have the yearly maintenance. Don't open it. Leave it.
Okay, that's a
Let it
good
run.
there you
Mhm.
go. I like that. So, probably the last one for me is like troubleshooting in the field. So, can you tell the difference between like cavitation or vapor locked or mechanical wear or system design problems when you're going in and listening to the compressor? I mean to the pump. Like, how do you differentiate really between these different issues, like mechanical wear versus cavitation? Can you?
Well, cavitation, you heard the sound. There's a sound. The pump start vibrating. It's one more situation. I don't talk about this. It's vapor entrainment. Means when you change the load in the system too much, you create on the idle impeller, you create a vapor in the idle impeller. Means you're not pumping too much gas, too much liquid to the system. For example, in the 100 gallon per minute. For some issues, you overload the system. You treat the hot gas. In some points, you see the pump makes some noises, really nice noises, but there's no cavity. You check the amps, and the amps reduce. Means the impeller, the eye to the impeller is getting gas on the eye of the impeller. Means you're not pumping the mass flow design the pump. You're not pumping 100 gallons per minute. You're pumping 80 gallons per minute. Means, yeah, the production say, hey, we don't have liquid in the coils. I can able to reduce the temperature. What's happening? Go to the compressor, check the valve, but then not check the pump. When you have overload the product to over, for example, the product is going to enter 35, 40 Fahrenheit, the product to the freezer. Okay, you put it 40 Fahrenheit is a recommendation, or 36 Fahrenheit. But in some points, say it's 50, 55. I said, I don't care. Load it and close the door and run it. Or the freezer is size for example, 10 pounds of product and you put 12 pounds and overheat it. You can get those load changes inside the system. And because in some point you not go to 1 psi per minute, but you go very close, point 0.8, point 0.7 psi per minute. Means when you have those very close, those pressure drop very close to the limit, means you create this eye on the pillar and you cannot have liquid in the system because you create vapor, no cavitation, vapor inside the impeller of the pump. The way to detect it, get the amps and you see the amps reduce and you don't have liquid in your vessel in your system means you do something wrong. Okay, that's
Yeah,
one more point.
that makes sense. Another question here: do they have to install the Q-min orifice in the discharge line, or what happened if they don't install the Q-min orifice? And you showing so I think
Oh,
that's just specific to yours, right?
yes. The only thing I not recommended to install the Q minutes is a transfer pump for the low side to the high side because you run the pump for very short time. When for the vessel is getting too much liquid, you run into empty the vessel to send it to the high side. Is the way I recommend it. When you have the system constantly running for the loads, you're changing the loads on the system, liquid up and down, the system demanding too much liquid, less liquid, and you have little flash gas. The cumin or the need to be installed to prevent those and prevent the pump damage. Need to
Yeah.
is mandatory. Mhm.
Yeah. And there's another question here. I think you answered the maintenance schedule and the manual manufacturer. You say if it's running good, amps are good, flow is good, do not open it.
Don't touch it.
Don't touch it. That's
Don't,
your
don't mess it
recommendation.
up with the pump. Yeah, because
Yep.
most of the problems say I want to open the pump, and after I take close it back, it's a problem.
Yep.
Leave it run. Leave it run. Mhm.
Okay. Ernesto, thank you so much for this. I learned a
No, you're
ton. How can
welcome.
people find out more about you, more about your company to if someone wants to reach out and learn more from you?
Well, you can go to LinkedIn and see my profile, or you can go direct to the webpage to hermetic.
Hermetic.
Okay. Yes. What is
Yep.
okay? Yeah, I forgot.
Yeah, that one there.
Okay. You
Yeah,
can
go
go to
there.
Hermetic, and send an email or send detective who is the regional office and send an email you want to
Yep.
contact. For example,
That's
contact and you see US and you can get the information for our office. Okay. Hmm.
amazing. Ernesto, I
Hmm.
want to thank you so much. I want to thank everyone for taking the time, all the questions you asked. This is just the beginning. This was a huge kickoff to CO2 Unfiltered. I want to thank you, Ernesto. Next week, we got Sam Major, and we're going to be diving into before you service a CO2 condensing unit. Here's what you need to know. Sam Major's from Turner Piping, and I'm super excited. Like he installed tons and tons of CO2 condensing units. I'm pumped up for that. So don't miss that next week. If you have friends who want to join and learn about CO2 condensing units, how to install them, how to service them, how to troubleshoot them, this is what we're all about. And as always, my name is Troy Matthews. Let's get a conversation going. Thanks, Ernesto.
Thank you, everybody. Bye bye.